let's recap the method on using vertical slices to compute area. The first thing you need to make sure before you start anything is that your curves are labeled as y equals a function of x. If that's not the case, then you need to isolate y. Then you'd find all intersection points algebraically. That helps you start the sketch. Between each pair of consecutive intersection points, find top and bottom. So you have 2 points of intersection. You need to figure out which curve is on top, which curve is underneath. To do that, you need to take a point between the two and evaluate both. So by evaluating both at both functions at a point between these intersection points. Then you can give a rough sketch of the region. What's important is you have the right intersection points and the right curve bounding the region above and bounding the region below. That's going to ensure that your integral is set up well. Then you label all curves and intersection points. Now you're going to set up the integral. It's going to be the integral from a to b of top minus bottom. And one thing that we haven't seen yet, but that we'll see next, is you need to split the integral up whenever top and bottom switch. All right, so we'll do a case where there are more than 2 intersection points, and in the middle of the region, the 2 curves kind of intersect and pass through each other, and top and bottom switch from one curve to the next. So something like this would be like that. All right, so here's a helpful picture to understand the formula. Think of the region as being built from thin vertical rectangles. So in the proof of a formula, we use regular rectangle, but we use n of them. When we did the limit as n goes to infinity, you could think of them as shrinking the width of the rectangles until it's really just a little stick. All right, so let's draw one of these sticks. So you are going to think of this region as being built of infinitely many of these thin strips. These are called vertical slices. These are vertical slices. All right, so each of these vertical slices has width. Well, the width usually is delta x, but if we think of it as being infinitely small, I'm going to call it, I'm going to do just this. It's going to be dx. And then the height is going to be whatever function gives you top minus whatever function gives you bottom. All right, so it's top minus bottom. And so the area of one of these strips will be top minus bottom dx. Right, now we want to add them up. We're going to call this dA if you need a name for it. We're going to add them up. So usually you add them up with a sum when you do Riemann sums. But here, because there are really infinitely many of them, what you'll need to do is you'll need to take a fancy sum, which we call the definite area. All right, let's try one more examples right here. So evaluate the total area enclosed by the curves y equals 4x and y equals x cubed. Give a sketch of the region including all intersection points. All right, so that's a typical question. Both curves are given as y equals a function of x, so that part of the method doesn't require any work. So the second step was to find intersection points. Right, so I have y equals 4x equals x cubed. Again, if you feel comfortable, please stop the video and try it on your own. Otherwise, I would do it for you right here. I'm going to send everything to one side. And then I'm going to factor. It's tempting to divide by x, but you can only divide by things that are not 0. So if you divide by x, you'll actually get rid of one of the intersection points. All right, so I'm done factoring. I get 3 intersection points. I'm going to put them from left to right. I have -2, 0, and 2. Let's find the y values. So at -2, y is 4x. It's -8. You can use either curve to find the y value. I'm just going to use this one because it's the simplest. All right, so here's what we know so far. We know the curve intersect at 0, 0. 1, 2, 3, 4, 5, 6, 7, 8. And they intersect at 2, 8. And at -2, -8. Right, so my region is going to be somewhere here. I'm going to need to figure out which curve is on top, which one's underneath, between -2 and 0. So let's do that. So from -2 to 0, I'm going to plug in a point between the two. I'm going to plug in -1 just because that's a nice integer. So at x equals -1, the first curve is 4x. That's going to be -4. The other curve is x cubed. That's going to be -1. Right, so I'm going to use blue for this one. I'm going to use green for that one. So we said -4, so 1, 2, 3, 4. This is the green curve, and the blue curve is at -1. All right, so we know that the blue curve is above the green curve at -1. That means it's going to be above for the whole region. Not the whole, sorry, the whole interval here until the next intersection point. All right, the curves cannot switch from top to bottom without cutting through each other. And so here I have my first section of my region. Now we have to do the same thing between 0 and 2. I'm going to plug in 1. The first curve is going to be at 4. The other one's going to be at 1. So I have the blue curve is at 1. Sorry, different blue. And so it's going to look something like this. The green curve is at 4, we said. So it's going to be something like this. And so I have a second piece right here for my region. All right, so looking at this region, you could see that if I'm trying to figure out what top is, sorry, it's a color we've already used. Let's use purple. So I would use the blue curve from -2 to 0. Then, I would use the green curve from 0 to 2. If I was looking for what bottom was, yellow I haven't used, I would use the green curve from -2 to 0, then I would switch to the blue curve here. All right, so when I set up my integral, I want to say it's the integral from -2 to 2 of top minus bottom. But in this case, I do not have a single formula for top. The formula depends on where I am. So I won't have a choice but to split my region here when top and bottom switch. I'm going to look at this part first and then this part second. And then for each of these two parts, I'll be able to choose top and bottom. So I will say it's the integral from -2 to 0. And on that range, we have top right here. So that's x cubed minus 4x dx. And then for the second part of the region, from 0 to 2, top is going to be 4x, and bottom is going to be x cubed. I know you guys know how to integrate these, so let me just give you the answer. That way, if you want to practice a bit more, you can try it. It should give you 8. Right, so the total area is 8. In fact, each of the two pieces would give you 4. All right, so that's it for this video. In the next video, we'll be looking at using horizontal slices, and that will apply to a different type of region.